Welcome to Tellefsen Physics. So what we're going to do today is we're going to take a look at the periodic table and be able to identify the subatomic particles that are present in every atom. In addition to that, we're going to look at what the outer shell of electrons has, because that turns out to be the most important thing regarding how chemical reactions and chemical properties occur. So what we're going to do is we're going to look at periodic table. So this is a website, ptable.com, that shows the periodic table. Now, periodic table took a while to put together. A number of different scientists, including Mendeleev, put together these elements based upon properties that they saw. And they noticed that certain elements had similar properties to other elements. And so over many years and many iterations, this is what the modern periodic table looks like today. And so right here at the top, we start with hydrogen and we move on from there. And so what we're going to do is we can look at one of these elements. So hydrogen is a great one to start with because it's the simplest one there. And so when I click on that, we see we've got a number up here, number down here. And so the number up here is known as the atomic number. That actually tells us the number of protons, so positively charged subatomic particle located in the nucleus of the atom. And that proton is what makes hydrogen hydrogen. Now, in a neutral hydrogen atom, if we have one positive charge from the proton, we're going to have one negative charge from the electron. So neutral hydrogen has one proton, one electron. So then what's this number down here? So 1.008. So that's known as the atomic mass. And what it's telling us is, for right now, we're going to round that to the nearest whole number, and that number is also 1. What this number tells us is that we have a mass of 1. Well, it turns out in the atom, the proton, which we've already talked about, but also the neutron, which is a neutral subatomic particle, has approximately the same mass as a proton. Those are the only ones that really contribute any mass to an atom. Electrons do have mass, but they're approximately 2,000 times smaller and are not really included in the atomic mass. And so if our atomic mass here is 1, and we have one proton, well, that means there's no neutrons, and hydrogen is the only atom that has no neutrons. We'll come back to what the 1.008 means. Now, one of the more important elements that we have, I'm going to click over here in column 14, is the carbon atom. And so the carbon atom has an atomic number of 6 located here at the top, so it means it has 6 protons. And when it's a neutral atom, it also has 6 electrons, so that it matches up. Notice that the atomic mass, if we round it to the nearest whole number, is 12. So now this is a case where we have to figure out how many neutrons and protons are in the atom. And so if I switch to here, right, so carbon has 6 protons. Now, its mass is 12. And so when we look at atomic mass, we're thinking about protons plus neutrons. So if the number of protons based upon the atomic mass, number, based on the atomic number is 6, and the atomic mass is 12, well, 6 plus 6 equals 12. So this particular atom has 6 protons and 6 neutrons. Now, one other thing that I want to point out, go back to our periodic table, and this got slid down, so let's slide it back up. This is in column 14. This actually becomes important. And actually, what we see over here, there's a number 2 and there's a number 4 on my big carbon tile right here. Well, now what that is doing is it's referring to the number of electrons that are in each energy level. So the way the periodic table is set up, hydrogen and helium are in the first row. And so there's only 2 possible electrons that fit in the first energy level. The next one, 1, 2, 3, 4, 5, 6, 7, 8. 8's going to be a big number for us. So 8 electrons fit in the next shell. But there's only 6 total electrons in a neutral carbon atom. And so we've already put 2 in the first row. So the next row has 4. This is, outer shell is what we call the valence shell. And that valence shell is what's going to be really important in how carbon interacts with other elements. Now I want to show you an example of when the neutrons and the protons are not the same. So let's pick sodium. All right, so sodium has an atomic number of 11. So that means it has 11 protons, and when it's neutral, 11 electrons. But if we round the atomic mass from 22.99 up to 23, we need to figure out how many neutrons there are. So let's go back to here. And so with sodium, the mass is 23. And the atomic number, so I'll write it this way this time, is 11. And so that is the number of protons. So how many neutrons does there have to be? Well, 11 plus 12 equals 23. And so the number of neutrons in a sodium atom is going to be 12. And as you go up the periodic table, you're going to find that the number of neutrons gets larger and larger and larger. And the number of neutrons is actually going to dictate the stability of an element. Now, one last thing I want to mention is, let's go to carbon, since carbon is our building block of life. And let's look at that 12.1001. So it actually says the atomic mass. So carbon atomic mass. So I rounded it before, but it's 12.011. So that is actually a weighted average. A weighted average of what? Well, it turns out that elements exist with different number of neutrons. And so what do I mean by that? And so different number of neutrons. So carbon 12 has exactly an atomic mass of 12, which means this has 6 protons plus 6 neutrons. And this is in approximately 99% abundance of all carbon atoms, approximately. Then there actually is also some carbon 13 and some carbon 14. And so carbon 13 is approximately 1%, and carbon 14 is like 0.001. Not exactly sure off the top of my head. And so what does that mean? Well, the number of protons for carbon never changes. It's always 6. But it turns out about 1% of the carbon that exists has 7 neutrons. And a little bit, and carbon 14 turns out to be radioactive actually, has 8. And so now you start to get to a point where the atom, it's harder for it to hold together. So what happens is, so this has a mass of 12, and there's 99% of it. So there's 99, which means 0.99. And then I add 13 times 0.01%. And so what that will give me is a number that gets close to this. And so when you look at numbers on the periodic table, what you're actually looking at is the mass is an average of all of the different isotopes that exist. All right, so one last thing that I want you to be able to do is, let's pick, what should we pick? Let's pick phosphorus. All right, so I want you to come up with the number of protons, electrons, and neutrons plus the number of valence electrons. You can pause the video if you need to think about it for a moment, and I'll reveal the answer when you restart it. All right, so if we look at this, the atomic number is 15. So it has 15 protons, and if it's a neutral atom, it has 15 electrons. The atomic mass, let's round it to 31 for this purpose. Now obviously it has some other stuff, in this case some phosphorus 30, but let's focus on phosphorus 31. And so 31 is the number of neutrons and protons. So if there's 15 protons, there's got to be 16 neutrons. And then the number of valence electrons, it's listed on this periodic table, but a regular periodic table won't have that. It's in column 15. So it turns out you drop the 1, the number of valence electrons for this entire row is 5. Just like over for carbon, the entire row is 4. And actually we didn't talk about it, but for hydrogen, the valence electron is 1. That entire row is 1. So these column headers actually tell us how many valence electrons are in each one. All right, so look at some others. This ptable.com will actually help you answer some of the questions that I just talked about.